Hey there, Stat 200. This lesson's all about comparing two groups with hypothesis testing. So we should already have covered a little bit on hypothesis testing in the previous lesson, and now we're going to just extend it a little bit into two groups, just to show that we basically have the same concepts holding. So let's just dive in. It's known that for right-handed people, the dominant, right hand, tends to be stronger. For left-handed people who live in a world designed for right-handed people, the same may not be true. To test this, muscle strength was measured on the right and left hands of a random sample of 15 left-handed men, and the difference, left minus right, was found. The alternative hypothesis is one-sided, that is, that the left hand is stronger. The resulting t-statistic was 1.90. Now, assuming the conditions are met, based on the t-statistic of 1.90, the appropriate conclusion for this test, using an alpha equal to 0.05, and using the t-table, is what? So you may see this here, I actually have two question sets. So we have the same setup, but I actually have two different questions that you could possibly see on the quiz and the midterm, and it's good to just get both different modes of asking questions in this setup down so you guys can see what you're supposed to do in each. So let's begin with the top one, and I'll actually make answering the bottom one very easy. So we're going to look at this t-table here. So what's the critical information? Well, first thing to remember, in the t-table, the sample size is important. The sample size gives us the degrees of freedom. So the degrees of freedom may sound really fancy, and if you go continue on in statistics classes, you'll see degrees of freedom basically says how much strength we give our observed information. And the way that we've done it here, the way that we're going to use in this class, is we're just going to use the degrees of freedom of sample size minus 1. So in this case we have a sample size of 15, which means we have 14 degrees of freedom, right? And we also have a t-statistic of 1.90 and an alpha level of 0.05. Now when we have an alpha of 0.05, that means that we are using the 95% confidence level, okay? Okay, and with that information, we can now hop on down to this table. So, when we look at this table, we have 14 degrees of freedom, which means we're only going to restrict what we're looking at to this row right here. Okay? So we've got that row. We're at 95% confidence, right? So we're going to see where those intersect. 95 comes down to here, 14 is right here. So we have this value, 2.145. That's what we got from the table, 2.145. Now what does that mean? Now, if I go back up, we have a test statistic of 1.90, and the way this t-table works is if the absolute value, that is whatever number you have here, just make it positive, the absolute value of your t-statistic must be greater than the value in the table in order for us to have a statistically significant result. Right? So, when we went to the table, using this here and this here, we found that the t-statistic that we needed to have to surpass in order to have statistical significance was 2.145. But the t-statistic we have is 1.90, so therefore it is not statistically significant. I think this question tends to trick people because there are two options that have us choosing statistically significant and one that says not, and people tend to narrow it down by saying, oh, well, there are two of these, so that must be it. It must be one of those. In this case, that's a trick. The results are not statistically significant, so there's not enough evidence to conclude the left hand appears to be stronger. Alright? Now, if we look at the second part of the setup, this is actually a little bit, almost exactly the same. First, we're going to test your knowledge of degrees of freedom, and then we test whether or not the p-value is greater than or less than 0.05. So, we already talked about how the degrees of freedom here is 14. Now, why would some people think, oh, maybe it's 28? The reason is that some people think, oh, 15 people, but we took 2 measurements on each. So that's 15 and 15, so there would be 14 and 14 degrees of freedom for a total of 28. You don't need to do that in this case, because this sample, quote unquote, is paired, right? You're not taking readings on two different people, one from a left-handed, one from a right-handed, or one from a left-handed man's left hand and another one from a different left-handed man's right hand. That would be an instance where you use two sample, and you have to go through a slightly more complicated calculation of degrees of freedom. That's in the notes, but it's not really going to be tested. Not heavily, at least. Some of you may see it in a variation of the quiz, but what's really important is that you realize that this is paired. So the degrees of freedom is a simple n minus 1. Let's take my word on that one. We already decided that it wasn't statistically significant based on the table. What I could have said is that at that alpha level, we're looking at these p-values, if you have a test statistic greater than 2.145, remember that's the value we found, then that means that your p-value is less than this. But we didn't have that, okay? So we had degrees of freedom 14, p-value less than 0.05? No, because that would be statistical significance, so that's not right. We have degrees of freedom 14, therefore the p-value is greater than 0.05, and the null hypothesis cannot be rejected. It's important that you understand all parts of this. The degrees of freedom, how the p-value plays into it, and what you do with the null hypothesis in that instance. So there's a lot to think about. So just make sure you review that. If you want to, take a minute, go back on what I was talking about before, and make sure you really hammer it out. We're going to talk some more about null and alternative hypotheses coming up. So, the second question. Now we're talking about the maximum distance at which a highway sign can be read. Okay? So, it's determined that for a sample of young people and a sample of old people, right, we have this value. You know, young people can probably see the sign further away because their eyesight, on average, is probably better, right? So they could probably see it at, 100 feet, whereas older people maybe can only see it at like 60 feet, something like that. Just to give you an idea of what we're talking about. The mean distance is computed for each age group. What is the most appropriate null hypothesis about the means of the two groups? Remember, the null hypothesis basically says there's no effect. There's nothing special going on in the population. We're not going to make any kind of hypotheses about the sample because we already have the values for the sample. We don't need to guess. Right? A hypothesis is just an educated guess, but we already know all the information. There's no guessing needed. So that right there eliminates this one and this one because we're not going to make any kind of hypothesis about the sample. That's a very important concept, and it trips up a lot of people. So now we're only here. Population means are different. Population means are the same. Now, like I said, population or null hypothesis means nothing special is going on. There is no effect of being in one group or the other. Or, another way to think about it is the means are the same. Okay? So that is really the key concept here. A null hypothesis, especially when you're comparing two groups, is that the means or the proportions are the same. Now that's actually the same thing, and you might see different notation on this. That's the same thing as saying that the difference in population means is 0. Right? If the difference is 0, they are the same. So this is the answer. And it seems like a simple problem, but I choose these problems because they're problems that many students get wrong in the past. So let that kind of speak to why I'm putting this on here. Null hypothesis, the population means are the same. All right. The level of significance associated with a significance test is the probability. So, we've already talked about p-values, what a p-value means. So how does the level of significance kind of play into that? How is that related? So we talked before when we had a level of significance of 0.05, right? So when we let's just read the answer options. We can talk about what's going on there. So the level of significance associated with a significance test is the probability of rejecting a true null hypothesis, of not rejecting a true null hypothesis, that the null hypothesis is true, that the alternative hypothesis is true. So let's think about the definition of the p-value. The p-value, if you recall this, is the probability that we observe the data that we see, or data more extreme, given that the null hypothesis is true. So, right away, if we think about it in that context, I mean, this one should be pretty clearly out, right? We're not talking about that. And it doesn't even make sense, you know, if you have a p-value that's low, that's very low, say 0.01, that's not the probability the alternative hypothesis is true. And actually, if you have a p-value that low, you start to think that it's more likely that the hypothesis is true, not less likely. So that one can't be it, right? That one just can't be it. Now, this one also doesn't work, and the reason is because as statisticians, it's very, very unlikely that anyone's ever going to say, this is true, right? We won't say that. We'll say, using kind of language like this, you know, we reject the null hypothesis, or we fail to reject the null hypothesis, but we're not saying the null hypothesis is definitely true, right? We don't want to get caught in any irregular data, or data that was written down incorrectly, or maybe somebody's messing with your results. It's just safer and more correct to not make any kind of hardline statements. So this one's definitely out for a couple of reasons. First is that it's a hardline statement. Second, it's not the probability that the hypothesis is true. That's not what a hypothesis is telling us. That's not what a p-value is. Although, as the p-value gets lower, the chance, you know, the likelihood that the null hypothesis is true does go down. That is true. But we are never, we don't make any kind of statements about whether or not it's true. We're just looking at the data saying, maybe true. Okay. So let's look at these two here, of rejecting a true null hypothesis, of not rejecting a true null hypothesis. So if a p-value is low, let's say it's 0.01, that would mean we have about a 1% chance. Now, is that a 1% chance of not rejecting a true null hypothesis? Or is it a 1% chance of rejecting a true null hypothesis? Well, if it's that low, you're going to reject, right? That's just the way it's structured. So the correct answer here is it's the probability, it's the probability of rejecting a true null hypothesis. Remember, when I defined the p-value, I said given that the null hypothesis is true. That automatically restricts us to these two answer options. And then you just need to think about it. It's not, if you get down to low p-values, you reject the null hypothesis, right? So this is the probability that you reject the true null hypothesis, and that's actually why the significance level is typically set at 0.05 or 95% confidence, right? Because once you get below that, you're saying, okay, well, I'm going to do this level of significance test. You know, I'm going to do this hypothesis test, and I'm going to set my level of significance at 5%, which means if the data, you know, produces a p-value that's lower than 5%, or, you know, anything lower than 5%, the maximum chance that I'm wrong, the maximum chance that I'm rejecting a true null hypothesis is 5%. Okay? So that's a tough one. But again, it really helps to just, this is the answer, think about it for a little while. Think about what happens when your p-value moves. All right, moving on. Researchers want to see if men have a higher blood pressure than women do. A study is planned in which blood pressures of 50 men and 50 women will be measured. what is the most appropriate alternative hypothesis about the means of men and women? Now, this is very similar to before. Remember, the null hypothesis is that they're the same, and we're not talking about samples, right? We're talking about populations. The null hypothesis is the population means are the same. Therefore, the alternative hypothesis is not that. It's the other one. In that case, that's this one. Okay? That kind of ties in with what I was saying before. Null, things are the same, everything's equal. Alternative, something's different, something's going on. Okay? That's all I have this week. Take a look. Let me know if you have any questions. I'm here for you guys. Have a good one.